we continue with the special conditions related to the analysis of cable. Special conditions related to analysis of cables. So what are the special conditions? First we deal with condition 1. So equivalent capacitance measured between R phase and Y phase conductors further is with B phase conductor located on the sheath. So you have the R phase, you have the Y phase, B phase is located on the sheath. So you locate the capacitors now, CS, here it is CS, and between these two how much? It is CC. Now we have to find out what is the equivalent capacitance measured between R phase and Y phase conductors. For that we draw the equivalent circuit between R phase and Y phase, and you provide the B phase or sheath here. What about between R phase and sheath? R phase and sheath we are having CS. Y phase and sheath you are having CS. Sorry, R phase and sheath you have CS. Next to check Y phase and sheath you are having CS. Between R phase and B phase we are having CC. Between Y phase and B phase again you have CC. Between R phase and Y phase you are having CC. So this is the equivalent circuit. So you have between RB, CC, YB also CC here. R sheath CS, YS also CS only. Between RY it is CC. Now capacitors are in parallel. If capacitors are in parallel, what you do? Add their values. Adding them how much? CC plus CS. And to that what is in parallel? CC is in parallel. Now capacitors are in series. If capacitors are in series, what you will get? CC plus CS by 2. And finally the capacitors are in parallel. Again you add them. So how much? 3cc plus CS by 2, that is C0 by 2. So whenever in a question you are asked to calculate what is the equivalent capacitance between any pair of conductors, here we have calculated between R phase and Y phase conductor. But in general, the equivalent capacitance between any pair of conductors, how you calculate? It is given by C naught by 2. It is given by C naught by 2. Now we have condition 2. Equivalent capacitance measured between bunch of the conductors, that is RYB, and sheath. So where the RYB conductors are, all the three are bunched together. R, Y, B. All these are bunched together. Next we are having the sheath here. So we have the capacitances only between a phase conductor and a sheath. CS, CS, CS. So we have capacitance between a conductor and a sheath. So now when you draw the equivalent circuit, you provide the bunch now. RYB forms a bunch. Now you have sheath. What you have between R and sheath? We have CS. Y and sheath? We have CS. B and sheath? You have CS. So three capacitors in parallel. So what is the equivalent capacitance between bunch and sheath? You get 3 CS. So what is the equivalent capacitance you get? 3 times CS. So the capacitance between a bunch of RYB phase conductors and sheath, how much it is? 3 times CS. So now we discuss the third condition, that is equivalent capacitance measured between R phase and Y phase conductors bunched together and B phase conductor. So where they are bunched together and B phase conductors. So we draw the equivalent circuit. Before that, what about R phase, Y phase? They are bunched together. B phase conductor is as it is. So R phase and Y phase conductors are bunched together, and now we have B phase conductor. So what is the equivalent capacitance now? R phase and sheath CS, Y phase and sheath CS, B phase and sheath CS. What about YB? CC. What about RB? Also CC. Now we draw the equivalent circuit now. Form this R and Y. R and Y forms a bunch. Now we have to find with respect to B phase. In between you locate the sheath. What about R and sheath? It is CS. Y and sheath, again it is CS. B and sheath, again it is CS. R and B, how much? CC. Y and B also same, CC only. Between Y and B also it is CC. And now these two capacitors in parallel. So now we simplify this one and find what is the equivalent now. RY is bunch and he have B here. And CC and CC are in parallel. In parallel means what you will do? Add them, you get 2CC. And CS and CS in parallel. How much you get? 2 times CS. Next we are having other CS here. Now 2CS and CS are in series. So what is the equivalent you get now? So 2CS and CS are in series now. So you get 2 by 3 times CS. To that what is in parallel? 2CC is in parallel. So lastly, what is the equivalent capacitance between the bunched R phase, Y phase conductor and B phase conductor? You add these values now. So 6CC plus 2CS by 3. Take out 2 common. You get 3CC plus CS. How much 3CC plus CS? It is C naught. So R phase, Y phase conductors bunched together and equivalent capacitance measured with respect to B phase conductor. What is the answer now? 2 by 3 times C naught. 2 by 3 times C naught. So this is the condition 3, where R phase, Y phase conductors are bunched together and equivalent capacitance is calculated between the bunched R phase, Y phase conductors and B phase conductors. Now we deal with the last condition 4. So equivalent capacitance measured between R phase, Y phase conductors where they are now bunched together on the sheath, and between where you are measuring now, measuring on the, and what is the next one? B phase conductor and B phase conductor. So equivalent capacitance measured between R phase and Y phase conductors bunched together on sheath and B phase conductor. So R phase, Y phase are on the sheath and B phase is as it is. Locate the capacitors now. Between them CC and here it is CS. So now R, Y sheath, R and Y are bunched, and moreover where they are bunched on the sheath. Next we have B phase. R to B, what we have? CC. Y to B, what you have? CC. B to S, what you have? Again CC, CS. So what is the equivalent capacitance now? Between that bunch and B phase, capacitors in parallel, add them. So this can also be written as C0 minus Cc. So this can also be written as C0 minus Cc. So this is how you analyze this condition 4. Now you solve this common data question. The test results for 1 kilometer how much now? 0.7 microfarads between one conductor and other two conductors bunched together with earth sheath and 1.2 microfarads measured between three bunched conductors and a sheath. Now first part of the question is capacitance between any pair of conductors with sheath isolated is. So how to calculate? So 0.7 microfarads between one conductor and other two conductors bunched together with earth sheath. The condition 4. Please refer condition 4. We have R phase, Y phase bunched together on the sheath. And we have measured with respect to B phase conductor. What it is? 2 Cc plus Cs is 0.7 microfarads. And 1.2 microfarads measured between three bunched conductors means 3 Cs. So from this, what is Cs? 0.4 microfarads. So 2 Cc plus 0.4 is 0.7. From this you calculate Cc, 0.15 microfarads. And now you want capacitance between any pair of conductors with sheath isolated. Any pair of conductors means condition 1. In condition 1, we have calculated equivalent capacitance between R phase and Y phase conductors. Here we want to calculate between some pair of conductors. So what is the answer now? It is C0 by 2. What is C0? 3 Cc plus Cs. So 3 into 0.15, Cs is 0.4 by 2. So on simplifying this one, you get 0.425 microfarads. Now second part of the question is, the charging current when cable is connected to 11 kV, 50 Hertz supply is. So how to find out what is the charging current? Omega C0 V phase. How much C0 is? 3 Cc plus Cs, you get 0.85 microfarads. What is line voltage? 11 kV. Phase voltage is by root 3. So on simplifying this one, you get the answer 1.695 amperes. So you get the answer as 1.695 amperes. Now the next question. The capacitance measured between any two cores of a three-phase cable is 0.3 microfarads per kilometer. The charging current and charging volt ampere taken by 5 kilometer length of this cable when connected to 11 kV (50 Hertz) supply is. So this is what we have to calculate here. So how to find what is the charging current? First we observe the capacitance measured between any two cores. Any two cores means between any two phase conductors, CRY. How much it is? C0 by 2. How much? C0 by 2. But CRY given as 0.3 microfarads per kilometer. Length of the cable is 5 kilometers. How much? 1.5 microfarads. From this, what is C0? It is 3 microfarads. So now we can find what is the charging current per phase. That is omega C0 V phase. F is 50, C0 3 micro. What is phase voltage? Line voltage 11 kV. Phase voltage divided with root 3. So on simplifying this one, you get 598 amperes. So on simplifying, you get the answer as 5.98 amperes. Now we can find what is the charging volt amperes. So we have to find out what is the charging volt ampere. Do you find for single phase or three phases? See, this volt amperes you calculate for the total three phase system. So for three phase system, what is formula? 3 omega C naught V phase square. So 3 into 2 pi 50 C naught 10 power minus 6. Now 11 kV. Line voltage by root 3 is the phase voltage. So simplifying this one, you get 114 kVA. So on simplifying this one, you get the answer as 114 kVA. So this next question, this from the IAS Civils question paper. A 1 kilometer long 11 kV 3 core 3 phase cable gave the following results. First result is capacitance between two conductors joined to sheath and third conductor. It is 0.6 microfarads. Next is capacitance between all three conductors bunched together and sheath. How much? 0.96 microfarads. So we have to find out effective capacitance of each core to neutral is. So how you find out with respect to any of the three phase conductors and neutral? You know the capacitance is CS. That CS we have to calculate. Now for that no need of having the first result. Second result is sufficient. Bunched together and sheath means 3 CS. 0.96. So what is the value of CS? 0.32 microfarads. So what is the value of CS you get? The value of CS is 0.32 microfarads. So this is how you calculate and find out this value here. So now we come across the additional terms in the analysis of cables. The next term is insulation resistance. Next we come across insulation resistance. What do you mean by insulation resistance? Which opposes the flow of leakage current through the dielectric is known as insulation resistance. So it is the resistance offered to the flow of leakage current through the dielectric is known as insulation resistance. So on simplifying and verifying, the insulation resistance Ri, you get the formula as rho by 2 pi L, natural logarithm of capital R by small r. So insulation resistance means the resistance offered to the flow of leakage current through the dielectric is known as insulation resistance. So you can also observe this point here, the insulation resistance, it is inversely proportional to the length of the cable. It is inversely proportional to the length of the cable. Now we solve this next one, is from GATE question paper. The insulation resistance of a cable of length 10 kilometers is 1 mega ohm. For a length of 100 kilometers, of same cable, the insulation resistance will be. So how much what is formula you write? Inversely proportional to this value. For 1 kilo ohm, 1 mega ohm, 10 kilometers. For 100 kilometers of the length of the cable, we have to calculate what is the insulation resistance. So Ri into 100, it is 1 into 10. So how much Ri is? 0.1 mega ohms. The value of Ri, you get it as 0.1 mega ohms. Now we solve this next one. A single core cable 5 kilometer long has insulation resistance 0.4 mega ohms. The core diameter is 20 mm and diameter of cable over the insulation is 50 mm. Insulation resistivity is so you know this basic formula. Ri is rho by 2 pi L natural logarithm of capital R by small r. So 0.4 mega ohms, rho you don't know. Length of the cable, how much given? 5 kilometers. And what about capital R? 25, small r is 10. From this you simplify and find what is R. You get 13.72 into 10 cube mega ohm meters. So this is how you find out what is the insulation resistance, and further the different methods of getting the coherence on insulation resistance. Now we discuss what are the losses in an underground cable. So now we check what are the losses in an underground cable. Now, a 3-core cable or a single core cable is subjected to different losses. Among them, the first loss we name it as a leakage loss. So the first type of loss is a leakage loss. Now why you get this leakage loss? It is due to the flow of leakage current through the dielectric. It is due to the flow of leakage current through the dielectric. So it is the power loss due to the flow of the leakage current through the dielectric. And why it occurs for both DC voltage and AC voltages? So it occurs with DC and AC voltages. Now next we come across the sheath losses. Now when you analyze the 3-core cable, why the sheath losses occur? Due to the magnetic flux linkages. Due to the magnetic flux linkages. Now you check a 3-core cable. What about in a 3-core cable? We have their corresponding fluxes, phi r, phi y, phi b. Sum of all this is equal to 0. So you don't have any sheath loss in a 3-core cable. But in case of a single core cable, this phi not equal to 0. Therefore what we say, the sheath losses occur in a single core cable. Whereas in a 3-core cable, the sheath losses do not occur. Sheath losses do not occur. Now the third one you come across is the core loss. The core loss is due to dissipation of heat during full load conditions. During full load conditions. So you know that the core losses increases as the operating temperature increases. And why the temperature increases? Due to the heat dissipation in cables during the full load conditions. During full load conditions. So this is regarding the third one, that is core loss. Now we have the fourth one, that is the dielectric loss. So represent a core here and represent a dielectric. Just like any material, dielectric also has its own resistance Ri. Now further you can observe core surface, sheath surface, two different potentials. In between dielectric, how to represent? You represent with a capacitor. So how you draw the equivalent circuit here? You connect a resistor Ri and a capacitor C connected in parallel. Now say the current flowing here is IRi, here it is IC. The total current is I. And what about this corresponding voltage? It is the phase voltage here. Now when you draw the corresponding vector diagram, how you draw the vector diagram? Consider the voltage as the reference vector here. You know, in the case of a resistor, current and voltage are in phase. So IRI and V phase both are in phase. In phase means we draw along the same axis in the same direction. What about IC? Current leads voltage by 90. So we say IC leads V phase by 90 degrees. So IC will be here. Now find the resultant of these two. You get the resultant current as I. Now indicate the phase angle between I and V phase, that is phi. And indicate the angle between IC and I. This angle is delta. And what you call that delta as? Delta, you say it as loss angle. And what is phi? Phase angle of power factor. Now if you apply tan delta, how much you get? Opposite side IRI, adjacent is IC. So from this, what is the IRI? IC times tan delta. And what is the charging current IC? Already we have written omega C naught V phase. Once you know this one, how you find the dielectric losses? That phase voltage multiplied with IRI. How much you get? Omega C naught V phase square tan delta. This is the dielectric power loss. Omega C naught V phase square tan delta. This is the formula to find the dielectric power loss. Also you check from the vector diagram, phi plus delta is 90. So how to write what is phi? 90 minus delta. Now if you know this phi, how to find the power factor? It is cos phi. You write it as cos 90 minus delta. How much it is now? Sin delta. So power factor of an underground cable, cos phi, is given as what? Sin delta. It is given as sin delta. So how you represent an underground cable electrically? An underground cable is electrically represented by connecting R and C in parallel. A simple parallel RC circuit. So an underground cable is electrically represented by a parallel RC circuit. So next we represent that an underground cable is represented by a parallel RC circuit. So this is how you represent the total analysis of RC circuits here. Now we solve this next question. This from the GATE question paper. So this is how you have to calculate here. You know the formula for the dielectric power loss, omega C naught V phase square tan delta. What is omega? 2 pi f. C naught 125 nanofarads per kilometer will be as it is. What is the phase voltage? Here it is the single core cable. So represent as it is, no divided by root 3. And tan delta tangent 2 into 10 power minus 4. So on simplifying this, you get 95 watts per kilometer. On simplifying, you get the answer 95 watts per kilometer. So this is how you calculate and find out what is the dielectric power loss here. So this whole square here. Next question is an 11 kV 50 Hertz single phase cable has a diameter of 20 mm an internal sheath radius of 15 mm. If the loss angle is 0.031 radians. Charging capacitance being 0.8225 microfarads, then the charging volt ampere is, again then the dielectric power loss is. So this is what we have to calculate here. So what is the formula for dielectric power loss? Omega C naught V phase square tan delta. Omega is 2 pi f. C naught 0.8225 microfarads. What about V phase 11 kV? Tan delta is 0.031. So these you have to calculate and find out what is the dielectric power loss here. So they are based on omega C naught V phase square tan delta. If you have a 3-phase cable, this is for single core cable. The previous question also single core cable. When you analyze a 3-core cable, you have to multiply with 3. You have to by default multiply with 3 to get the final answer. Now you have 5 minutes break. The first question is by Somdev from West Bengal. In condition 2, how we get the capacitance from the diagram? In the condition 2, all the three phase conductors are bunched together. Find the equivalent capacitance between the bunch and sheath. Next question is by Sanjog. In 7th, 8th questions, it is mentioned between any two coils is 0.3. It is not CC place. Very good question. It is not CC place. What they give in the question is between any two phase conductors, R phase, Y phase. Then we think, what about B phase? If not mentioned, by default take it as the sheath. The B phase conductor is located on the sheath. So that is CRY only. Next question is by Vishram from Agartala. In a three-phase underground cable, sheath loss is 0 only under balanced and not in unbalanced conditions. Yeah, you are correct. Next question is by Sanjog. In 13th question, V phase should be 11,000 by root 3. No, we are not dividing with root 3 because you are dealing with a single phase system. Line voltage, phase voltage, line current, phase current, everything same. But when you treat with a three-phase system, you come across line voltage, phase voltage. Next question is by Gaurav from Bikaner. Which components the stability is not affected in transmission line and why? Now stability depends on the phase angle, that is the load angle between rotor and stator. That is the first primary component. It is delta affecting the stability. Okay, we continue after the break.